Welcome. I'd like to do two paradoxes today. I'd like to prove that the value of pi is actually 2 and the value of the square root of 2 is also 2. Here goes. Let's start with a line segment, and I'm going to use this as the diameter of a semicircle. So that is, if I draw a semicircle as follows, we'll say then that this line segment has length 2r that I'm using as a diameter. Alright, so then what is the length of that red line I drew for the semicircle? Well, clearly that's half the circumference of a circle, so it's half of 2 pi r. 2's cancel. The length of that red line is pi r. Now what I'd like to do now is draw two semicircles under that red one. I'll do them in green, and I'll use half the diameter for each of them. So that means each of these green semicircles has radius r over 2. So what's the length of this green line? Well, it's two copies of the same thing. It's two copies of half the circumference, and in this case half the circumference is 2 pi, but the radius is half of r over 2. Well, I've got lots of 2's here. Two 2's on top, two 2's on the bottom. They all cancel, and the length of that green line is also pi r. But this is wonderful. Basically, this just has shown that if I draw a semicircle, I get one length of line, and if I choose to replace it by two semicircular bumps underneath it, I get the same length of line. The length of line is not changing. So that means if I was to draw two semicircular bumps under each of the green semicircles, whoops, my pen disappeared, 1, 2, and 1, 2, the length of that blue line, which keeps vanishing on me, must also be pi r by the same mathematics. And if I replace that again by two more semicircles under each of those semicircles, I'm going to get this little bumpy line here, which must again be length pi r. In fact, you can see, no matter how often I do this process, I'm always going to have a line of length 2r. And what does this line want to become in the limit? Well, clearly, pi r. So what does this line want to become in the limit? Well, clearly we're approaching the diameter of the original circle. So I guess we've just proven that the limit of all these values, pi r, wants to be the diameter of that circle, 2r. So, well, that's obviously a constant sequence. The limit of pi r is always pi r. I guess we've just proven that pi r must be 2r. Well, I'm pretty certain that r is not 0, so I can divide both sides by r, and I'm left with pi equals 2. There we go. You may have thought it was about 3.141 so and so, but it's not. Its pi is actually 2. Let's prove now that the square root of 2 is also 2. So everyone knows that the diagonal of a square is allegedly a value known as the square root of 2, though a lot of students might say otherwise at first. So let me draw a square of side length 1. And for those very beginning in mathematics, might think that this length of this diagonal line is actually 2. And you know what? It turns out they're right. Now you might say, I'm being silly because a quick Pythagoras tells me that 1 squared plus 1 squared would have to be x squared, so it tells me 2 is x squared, tells me x is the square root of 2. But you know, there's no paradox here because square root of 2 is 2, as I'm about to prove. Here goes. What I'd like to do is approximate this diagonal line by a little staircase of vertical and horizontal line segments, like follows. So there's a green staircase that approximates the diagonal. It's a pretty crude approximation here, but let's work at the length of that green staircase. Well, all the horizontal parts of the staircase, if you can see, match the bottom side of the square. So the horizontal parts add up to 1. And the vertical parts, here they are, match exactly the entire vertical side length of the square, which is also 1. So the length of that green staircase is 2. In fact, if I did a smaller staircase, like this, again, all the horizontal segments add up to 1, and all the vertical segments add up to 1. So the length of that's a finer staircase is also 2. In fact, it doesn't matter how tiny a staircase I do that just hugs the diagonal, all the vertical segments and all the horizontal segments each add up to 1, so it's going to be of length 2. Well, clearly, this geometric construction is approaching the diagonal of the square, which people claim is the square root of 2. So we must have that all these 2's, the limit of a whole bunch of 2's is 2. Square root of 2 then must be 2. That is, these staircases always have length 2, the diagonal of that line must also be 2. Voila, we have now proven that the square root of 2 is 2. Two little fabulous paradoxes, and actually they're both quite deep, and I'm just going to leave them hanging as a mystery. Can you resolve what's really going on in both these cases? Thanks.